Welcome back to this course on C programming and assembly language. We are in module 3. Last lecture we summarized what the desired features of our compilation process should be. So we essentially summarized that local variables is a good thing. You don't want to be tied down to using a unique name for every variable, right? So the concept of a local variable being local to a function is a very good thing. The scope of a local variable is also a very good thing, because the moment you enter it is alive and the moment you leave it's gone, right? So that is also a very useful thing. And the other thing we discussed is, because we have a limited number of registers in the microprocessor, we need to be able to pass function parameters as well in some other way other than through registers. So essentially we might want to pass as many parameters as needed, and for this we also discussed last time that it is probably best to push these parameters onto stack and pass function parameters as well through the stack into the called function. So in this lecture, before we go ahead and look at how a C program gets executed, right, and what more instructions we need to add, let us quickly understand how local variables and these function parameters could be accessed. So to remind you, we had this example where we had int g_ivar, which is a global variable. We had a main function, and the main had a local variable int z equal to 0 which translated to move z comma 0. Then there was a call function which took two parameters 2 comma 4, and we said we are going to push these onto stack using these particular instructions, right? We said we will pass them onto the function fn by pushing them onto stack using push 4 and push 2. So we are going from right to left, and then the function call gets translated using the call fn_address, right? Similarly, the function fn had another local variable called z as shown here, right, which is basically the same name, and we had to do some addition, and the function parameters x and y are now coming in as variables that are being pushed onto the stack. And of course, once we are done with the function fn, we do a return as shown here. So now the question is, how do I access these local variables? How do I access z? How do I access function parameters x and y in fn? So let us look at our function fn, which is as follows: int fn of int x comma int y, right, and there is a local variable int z equals 0 and z equals x plus y, and I am doing return of z. So now, given that we have established the fact that x and y and z have to be stored on stack, right, the question is, how do I access these? So the compiler, for example, when it sees this function fn, it knows that there are only fixed number of local variables. For example, in this function there is only one local variable called z, right. So therefore, what all that the compiler has to do is to allocate 4 bytes on the stack, right. Now here, for example, if I had another variable, maybe a and b, right, and maybe I also add to this another character char c, right, then the compiler looks at this program and says, okay, there are 3 integers z, a and b, and there is one character, right. So what it would do is, it would simply go ahead and allocate 4 bytes of memory for each z, a and b. So this would be my z, this would be my a, and this would be my b. And of course now there is a character c, so instead of 4 bytes it would simply allocate only 1 byte of memory here, okay. So this is 1, 4 bytes, 4 bytes and 4 bytes. These of course cannot be accessed in a last in first out manner, because you need to be able to do random ALU operations on these, and therefore the best register that can be used to access these variables is my EBP. So let us assume that my base pointer register is pointing here somewhere, EBP. Then it is quite obvious that this is EBP minus 4, this guy is EBP minus 8, this is EBP minus 12, and the final address is EBP minus 13, right. So what would the addresses of Z, A, B and C be? So the variable Z is going to be accessed as contents of EBP minus 4. The variable A would be accessed as contents of EBP minus 8. B would be contents of EBP minus 12, and C would now be contents of EBP minus 13. Note here, because Z, A and B are integers, these have to be D word pointers. So out here you would have to add D word pointer, and because C is a character, it is only 1 byte, I would have to add here byte pointer. So now how are X and Y accessed? So if you go back to the function translation that we did, before we called fn underscore address, push 4 and push 2 happened, right. So the stack pointer is getting altered through the push 4, push 2 and the call function address, and then the local variables are getting assigned here, right. So it is very clear that the function parameters that are being passed will be on the other side of the stack pointer, or if we initialize the base pointer correctly, it will be on the other side of the base pointer. Therefore, parameter X and Y, right. So let me use a different color for function parameters. X would be EBP plus some number, let me call it n. Y would be EBP plus n plus 4, because X is also an integer and therefore that is going to occupy about 4 bytes of information, right. So what actually happens is, out here if I just continue my stack from here, X would be assigned 4 bytes here and Y would be assigned 4 bytes here. So if you look at the base pointer address, this would be EBP, for example, EBP plus 4. So with that we are in a position to go ahead and do our preliminary compiler output generation, and then we will see what other instruction needs to be added. Okay. So this is what we had discussed. It is a quick summary. Before a function is called, parameters are pushed onto stack, parameters are accessed, function parameters are accessed as contents of EBP plus some offset, local variables are accessed as EBP minus some offset, contents of that, right. So we will come to the other points a little later. So here is an animation that we are going to go through now. in order to understand what other instructions are needed in order to complete this compilation process successfully. So, this is what we had discussed. The int z equal to 0 becomes move z comma 0, int function of 2 comma 4 gets translated as push 4, push 2 and then call fn, right. So, the address fn is whatever the function address is at linking time, that will get plugged in here, right. After we return the return value, let us assume it is going to be in EAX. So, that brings us to an interesting point. While we pushed function parameters and local variables on stack, the return values from a function can be only one value. You can only return one value and therefore, you do not have to return through the stack. So, we choose to return through the register EAX by default. So, if you are trying to return an integer from function fn, the function fn will load the return value into EAX, and after you return from the function fn out here, you just move the EAX value into your variable and you are done. Okay. Global variables, of course, g underscore ival is a global variable. You have no choice but to access them through an absolute address. Now, similarly, the function fn with int x comma int y gets translated like this, move z comma 0, z equal to x plus y gets translated to these move and add instructions, and once you are done with the function, you just do a return z. Okay. Note that here we are not doing a return n at this point. We'll come to where that is needed a little later, and also note that that return n has nothing to do with the actual return value that is in z. Okay. So, now let us go ahead and look at an animation where we look at all the segments, the code segment, the stack segment, the data segment all at once to see how this function is going to get executed in memory. So, the function main has a local variable, and I already showed you that the local variables are accessed as EBP minus 4, because there is only one variable now, there is only EBP minus 4, contents of that is my z. Okay. So, let us assume that this particular program was translated in such a way that the code segment address started in C100. These are arbitrary addresses that I am putting. I just need a label in order for me to refer to certain addresses. So, I am assuming that the move EBP minus 4 contents of comma 0 is C100, then there is C101 where I am doing the push, C102 is again the push of the second function parameter, and then I am calling the function fn, which I am assuming sits in C200, again it is an arbitrary address. So, before we start, let's look at the stack segment. I am assuming that the stack segment ESP and EBP are pointing at some arbitrary locations. We will see how to initialize them before we start the function main as well. Okay. So, we execute the first instruction, the arrow that is going to move here is the instruction pointer EIP. Okay. So, it has read the instructions from C100, which is move contents of EBP minus 4 to 0, okay, and you will see that wherever EBP is, EBP minus 4, that location gets initialized to 0, that is the local variable z. Now, I do a push 0x, how many over 0 is 4. Obviously, this is going to alter my stack pointer. It will move up, right, or it will get subtracted by 4 values, and the integer will get loaded onto the stack. Similarly, the second push is going to do something very similar, and the stack pointer moves up further. Now, when I try to do a call of C200, the microprocessor, as we discussed this earlier, knows during the decode phase of this call instruction that the next instruction where it has to resume from after returning is C104. So, therefore, before it transfers the control of the instruction pointer to C200, it will push on to stack the return address, which is C104. So, note that the stack pointer has implicitly moved by a large amount now because of various push and call instructions. Now the instruction pointer is loaded with the address C200, and we are assuming that our function Fn is sitting in this location C200. So now let us look at what happens here. First of all, as I already told you, any local variable will be accessed as EBP minus 4. So clearly, even before we start execution in this function Fn, our EBP is currently pointing somewhere in the local variable space of main. So in order to bring the EBP to the right context, I first need to move my EBP to the value of ESP. So that is the first thing, or a first instruction that gets added, and something that we did not discuss yet. Only when we go through this execution process we realize we need to do it. So EBP is now moved to ESP, and now I need to allocate what is known as the local variable space. So I earlier alluded to the fact that local variables are accessed as EBP minus 4 and so on. But what would happen if I just did a push or a call somewhere here? Because my ESP is pointing here, if I now did a push, it would overwrite my local variable space that is meant for the local variables of the function Fn. So in order to allocate local variable space, I first need to move my stack pointer far away so that there is no clash with my local variables that are being allocated here. Okay. Now how does the compiler know that 0x40, that is 64 bytes, is enough? Well, it knows it because the compiler knows exactly how many local variables there are in the function. So at compile time you can calculate how much of space you need and subtract the stack ESP with an appropriate value, right. So while we claim that the developer does not need to worry about allocating local variable space, which is a true statement, it does not mean that the compiler need not do that. The compiler does it by this particular instruction sub ESP, 0x40, which means the local variable space is now not going to be affected by any push or pop, because the top of stack is now pointing to after the local variable space. So now I go ahead and execute my function. Okay, remember that this function Fn also had a local variable z, which was going to be accessed by contents of EBP minus 4. Note that even in main, the contents of EBP minus 4 referred to the local variable z even there. But here I am now able to access a different variable because I have moved my EBP to ESP as my first instruction. So in some sense, the context for local variables is set by this precise instruction move EBP, ESP. So when we say that local variables have a context, they have a scope, that scope is set by this instruction of moving the base pointer to point to the stack pointer even before you enter that function. So you go ahead and do execute the instruction, right, move z, 0 is move contents of EBP minus 4, 0. Then I am going to do the addition operation of x and y. Note that x is nothing but a function parameter, which, as I told you, is going to be accessed as contents of EBP plus some offset. So I am going to access it as EBP plus 4. Why EBP plus 4? Because I had to push onto stack the return address when I did a call. So therefore the EBP is now actually sitting after the return address, which is C104. Therefore the function parameter 2 and 4 can be accessed only after that, which is EBP plus 4 and EBP plus 8. So I go ahead and execute my program. So EAX is loaded with the local variable x, then I am going to do the addition operation, and after that the contents of EAX will store my result of the summation x plus y. That needs to be moved into the local variable z, which is nothing but EBP minus 4, contents of EBP minus 4, and therefore you see that that location now gets the result of my addition, okay. And now I am done with my program, right. Earlier the return z simply did only one thing for us, it called the RET instruction. Unfortunately, if you now do the RET as is, the top of the stack is now pointing to some random location because we did local variable space allocation using the sub ESP comma 0x40. We need to undo this operation in order to return and get the stack pointer to the right value, right. So what do? We have to, for every operation on ESP, you have to do the counter operation on ESP before you return, otherwise you will have a random returning problem. So what you do is you add to ESP 0x40 and bring ESP back to where it was when you returned, okay, when you came into the function, sorry. So now you do a return and it simply gets back to C104. Remember that my stack pointer is now pointing to the top of stack is pointing to the data which is C104. So when you do a return, the top of stack is now popped into the instruction pointer which is C104 as indicated by this arrow, and the stack pointer is now incremented to come back to the original location, okay. So after returning from the function fn, I now need to load the return value which is x plus y, which was going to be stored in EAX, into my local variable z, which is addressed by EBP minus 4, okay. Now the issue is clearly EBP is now pointing to the local variable space of fn. Why is that? Because we have not brought our EBP back to our original value, right. Before we entered the main, EBP was pointing here to this local variable z, which means that when I did EBP minus 4, it would point to this local variable z. Unfortunately, because I have done a call and I moved my EBP to the local variable space of the new function, I am now accessing the local variable space of fn and not that of main. We have a bigger problem in fact, because we don't even know what our original EBP was before we altered our EBP in function fn. So that makes it a bigger problem because we can't even reset our EBP to come back here now, okay. Now is that all? Well, it turns out that there is another problem, right. So which means now you have basically done a stack corruption, in the sense you have accessed the stack of function fn even after returning from that function. So let us see what happens as I execute this program further. Remember that the global variable is set by absolute addressing, right. So EAX is moved into that, and now when I do a return, what will happen? Okay, remember that my stack pointer is pointing here, ESP. So when I do a return, the top of stack is going to be popped into EIP and execution will continue from there. So if I do that, obviously the return address is not 0x00002. So what have we done in the process of calling this function? We have pushed onto stack two variables with values 2 and 4, and we have forgotten to undo this stack operation before we did a return. and this is what we are going to correct in the next lecture.